In the next part of the class, we're going to look at two models describing the chemical bond using orbitals and what we know about quantum mechanics. Our starting point here is that real atoms and molecules are going to adopt the lowest energy or most stable possible arrangement of the nuclei and electrons. But just like when we thought about atoms, it's difficult to actually understand that fully because of quantum mechanics and the difficulties involved with all the electrons and all the atoms in our molecules. So valence bond theory and molecular orbital theory are two useful models that, again, are relatively simple to apply and will help us predict the properties of our molecules. Things like bond length, bond energy, the geometry. We'll see a lot of different applications here. The idea here, again, all models are wrong, but some are useful. So these are models but that aren't perfect in every way, but do a pretty good job of describing our molecules. Okay, so we'll start with some of the general principles. These apply to both theories. Real molecules adopt the lowest energy or most stable possible arrangement of nuclei and electrons. But how is that? Well, they're going to adopt a structure to minimize those electron pair repulsions. That's via CPR theory, which we've looked at already. Keep those pairs of electrons as far apart as possible. They'll repel to make the characteristic electron geometry shapes: linear, trigonal, planar, tetrahedral, and so forth. The new part here is this idea of forming the strongest possible bonds. So valence bond theory says that the best way we can form strong bonds is by maximizing the orbital overlap. That's a concept that we'll see also applies to molecular orbital theory when we get there. So valence bond theory is a nice extension of Lewis structures and VSEPR theory. We're going to describe bonds as being formed by atoms sharing valence electrons in overlapping valence orbitals. So hydrogen has 1s orbitals. When we bring two hydrogens together to form the H2 molecule, those 1s orbitals are going to overlap. And valence bond theory would say, let's think about the two electrons in that bond, right? Hydrogen, hydrogen, two electrons in that bond are going to be a spin up and spin down electron, and they're going to occupy this region right here where the hydrogen valence orbitals overlap. Here's another example for HF. So HF, if we look at that, we have a hydrogen atom with that 1s electron. Fluorine has a 2p orbital on it. We have a spin up electron here, a spin down electron here. When we bring those two together, we're going to now put two electrons into this space right here, where those two orbitals overlap. And again, one of our principles is we want to make the overlap as good as possible. This is a nice orbital overlap. We can see the two orbitals are colliding directly, and that will help us make a strong bond according to this model. So again, that's that key principle that we want to maximize the orbital overlap. And again, that does match experiment. We have a nice strong single bond between hydrogen and fluorine. Now let's look at something that's more complicated, like ammonia. So ammonia, if we had the Lewis structure there, looked something like this. And again, according to VSEPR theory, the steric number is 4, 3 bonded atoms plus a lone pair with 109 degree or less than 109 degree bond angles. But if we just think about the orbitals we have available in the atom, those are p orbitals for each of the 3 nitrogen electrons. And we think about having a px, a py, and a pz, p orbital. And we'd think about then putting the hydrogen atoms at those 90 degree angles to overlap the p orbitals with the hydrogen atoms on each axis, x, y, and z. But that doesn't match experiment. We should form a trigonal pyramidal NH3 molecule that'll minimize those electron-electron repulsions, and it actually would also allow us a little bit better orbital overlap, as we'll see. So what can we do? Well, valence bond theory says that to get something that matches our Lewis structure and our VSEPR theory, we're going to start mixing our atomic orbitals to form new hybrid orbitals in a process called hybridization. So the rules for hybridization: only orbitals in the same shell or the same end can mix. So 2s and 2p can mix, and in the third shell, 3s, 3p, and 3d can mix, but 2x can't mix with 3p. The next important thing is that when we form these hybrid orbitals, we're going to use up the atomic orbitals. So if I mix two atomic orbitals, I'm going to get two hybrid orbitals out, and the atomic orbitals are now gone. I don't have those anymore in the atom. I've mixed them and used them up. Similarly, mixing three orbitals in, I'm going to get three orbitals out. The principle here, n orbitals in, n orbitals out. Whatever orbitals I put in come back out. That will also apply to molecular orbital theory when we get there. Okay, so what do these hybrid orbitals look like? Well, this shows a picture of what would happen when we mix the atomic orbitals to form hybrid orbitals. So first we take the 2s and 2p on a particular atom to form an sp hybrid. So when we add the two together here, we can see we get constructive interference over here. These are both, say, positive. And here we get destructive interference, positive plus negative, giving you destructive interference, and we get an orbital pointed like this. On the other side here, when we add the two orbitals up, now we get constructive interference over here, destructive over here, and we get two orbitals pointed in each direction. We generally simplify this just to show the single sort of bigger lobe of the hybrid orbital, but that's what's happening. And what's nice about this is that these are pointed at 180 degrees. So if we formed those sp hybrid orbitals, remember we used up these two orbitals, they're gone. The energy here is just the average because we mixed one s and one p. The energy here comes out in the middle, and there's two unhybridized p orbitals left on each atom that are just sitting there that we could use for something else. Okay, so now let's do our first valence bond theory application. So here's BeCl2. Each time we do valence bond theory, we always start from the Lewis structure. It builds directly on that. So for BeCl2, beryllium's our central atom. The two chlorines go on the outsides. First, we can start with that skeleton structure. If we count up our valence electrons, we have 7 by 2 plus 2 is, what is that, 16 valence electrons. We've used 4 to make the skeleton structure, and that leaves us with 12 electrons left. We need octets on the outer atom, so 2, 4, 6, 8, 10, 12, and now we have our BeCl2 Lewis structure. We would like to get beryllium to an octet usually, but remember that beryllium is electron deficient, being in group 2, so we actually just leave the structure as is. Again, we could think about forming double bonds here, but because it's electron deficient, we don't. Next, how can we create orbitals to describe the bonding? So if we look at this here, now we want a description of what's going on. Well, we have 180 degree bond angles in beryllium, so this is a steric number of 2 is our steric number. The bond angles are 180. And again, this is actually a pretty good picture of what it looks like, just straight left and right. Now, we just talked about sp hybrid orbitals. sp hybrid orbitals are actually exactly set up to form these bonds. So this beryllium sp hybrid is pointed towards this chlorine over here. Chlorine, if we think about it, it has a valence shell. What is it? It's neon 3s2, 3p5. So it has 3p orbitals. And that chlorine 3p orbital, not my best drawing, but something like this. If we think about overlapping the sp hybrid orbital on beryllium with a 3p orbital on chlorine, that will let us describe the bonding. And the same thing would happen on the other side. So we have two bonds formed from these sp hybrid orbitals. The sp hybrid orbital on beryllium is overlapping with the 3p orbital on chlorine. Here's the same thing, just showing a picture, more 3D graphic with where those electrons are. Next thing about how we describe this, we can call this end-to-end or head-on overlap between those orbitals. The terminology on describing these different types of bonds, we have bonding orbitals which are symmetric along the internuclear axis are called sigma bonds. These sigma bonds have that end-to-end or head-on overlap. So these are all examples of sigma bonds, just the orbitals colliding directly. And we can tell by looking at the line connecting the two atoms if the electrons are along that line where they're overlapping, that's a sigma bond. That's the best possible orbital overlap between two orbitals, and therefore that's the strongest type of bond. So we will always want to make sigma bonds if we possibly can. The other type of bond that we'll look at in this class is a pi bond. That has a side-to-side overlap. That's not as good. We can see an example down here. Here the electrons are going to be located above and below the line connecting the two atoms. So we can see this overlap is not as good. It's sort of an glancing type overlap. It's that generally makes it a weaker bond. Okay, so just finishing our description of BeCl2, both of our bonds using this new terminology are sigma bonds because they're that direct head-on overlap. Next, let's look at what an sp2 hybrid orbital would look like. So this shows the process of combining one s and two p orbitals. If we remember, we had three p orbitals to start with, so there's also a pz orbital, but that's just going to sit here and going to stay available to us to do something else with. But these three orbitals are going to be mixed to form hybrid orbitals, and we can see these show a nice trigonal planar type arrangement of orbitals. When we think about the energy that we get out here, since we used these three, the 2p and the s, right, so we've used those three orbitals, the average of those three is the energy that we get out here, so three things sort of, closer to p than s, and we still have that, in this case this was a pz orbital that's just sitting here available for us to do something else with. Okay, so we won't show that process for all the other ones, but the other hybridizations that we have, if we mix the s and all three p orbitals, we get things arranged in this nice tetrahedral fashion at 190.5 degrees. If we had 5 orbitals, note that at this point, since we're out of p orbitals, the next orbital we have to include is a d orbital. That makes sp3d hybrid orbitals. Those are arranged in a trigonal bipyramidal type arrangement with 90 and 120 degree bond angles. sp3d2 would be the choice once you get to 6 orbitals mixed together, and those are nice octahedral type arrangements. So if we look at this closely, this agrees really nicely with our VSEPR analysis. This 180 degree angle, that's exactly what happens and what we want when we have a steric number of 2. When we have a steric number of 3, we're going to get trigonal planar electron geometry. And this is going to match up just with that. If our steric number was 4, we'd get this tetrahedral arrangement. Steric number of 5, we'd have trigonal bipyramidal. And steric number of 6, we'd get octahedral. So this goes really nicely along with analysis. When we think about forming these hybrid orbitals then, we can just add this right onto our VSEPR theory chart. If our steric number is 2, according to valence bond theory, we'll form 2 sp hybrid orbitals that will be arranged in just the right way to be used to form sort of linear geometry type bonds. And the same for each other option. So we really can just add this onto our VSEPR theory table. Okay, next let's go through the overall rules we get out for valence bond theory. On each central atom, we're going to form a number of hybrid orbitals equal to the steric number. That'll let us provide orbitals that agree with the molecular shape and electron geometry provided already by VSEPR theory analysis. Again, you can sort of put this on there and you can memorize it, I guess, but remember also if you know that rule that we're going to form hybrid orbitals equal to the steric number, you can also back it out. So for a steric number of 2, 1s plus 1p orbital is 2 hybrid orbitals. Steric number of 3, 1s plus 2p orbitals gives us 3 hybrid orbitals. If I need 6 hybrid orbitals, I do s, then 3p. I don't have like sp5 because there's only 3 p orbitals, remember. And then the remaining orbitals I dip into the d, so now I need d2. And again, that'll all add up. 1 plus 3 plus 2 gives us our 6 overall hybrid orbitals. Next, on each central atom, the hybrid orbitals are going to be used for lone pairs in the first bond to each neighboring atom, which will always be a sigma bond, which is our best possible and strongest overlap. The terminal atoms will just use the valence orbitals for bonding. On each central atom, any remaining unhybridized p orbitals are empty or are used for our multiple bonds. The multiple bonds, as we'll see, will always be pi bonds, which are worse overlap and are therefore weaker bonds. Let's apply those rules to look at BF3. So the first step in this is always we need to get the steric number, which means we need the Lewis structure and BSEPR theory analysis. So starting our Lewis structure, we have 24 total valence electrons. This is our skeleton structure if we now get octets on each of the fluorines. Okay, so let's check this 2, 4, 6 electrons for our skeleton structure, and then 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons to get octets on the fluorines. That leaves no electrons left over. We would want to get boron to its octet, but remember it's another electron deficient molecule, so boron is actually fine with 6 electrons here. Now we need the steric number. There's 3 bonded atoms and no lone pairs, so that makes the steric number equal to 3. Now that we can apply our valence bond theory rules, well, if the steric number is 3, that means I need 3 hybrid orbitals. I don't know why I can't write that. When I'm making 3 hybrid orbitals, I'll always use the S. I need 3 hybrid orbitals, so I'll use 2 p orbitals, and that together will make 3 overall hybrid orbitals. Next, the type of bonds. Well, the type of bonds are, since this is just that first bond between each atom, we're going to make sigma bonds. So these are 3 sigma bonds in BF3. This just shows a little bit nicer on a picture what that looks like. So the 3 sigma bonds are formed by overlapping the boron sp2 orbital with the fluorine 2p valence orbitals. And again, we could think about drawing the electron pairs like that up and down in those overlap regions. Okay, let's do one more example here answering these questions about NH3. First, the Lewis structure. There's the skeleton structure. We have 8 electrons. We've used 6, so 2 left over. That last lone pair, all the terminal atoms have octets, so the central atom nitrogen gets 1 more lone pair to get to an octet. Now, the steric number is 3 bonded atoms plus 1 lone pair is equal to 4. And if we apply our valence bond theory rules, that means I'm going to need 4 hybrid orbitals. To make 4 hybrid orbitals, what should I do? Well, I'll use an S, and then I need 3 more, so those will be all of our p orbitals. So sp3 is the hybridization. Just as before, if we want to think about the sigma bonds, well, the first bond between each atom is always that strongest sigma bond, so there are 3 sigma bonds in that molecule. Which orbital holds the lone pair? Well, we have 4 hybrid orbitals. 3 of them are used to make these sigma bonds. The 4th one is where the lone pair goes. Remember, according to the rule, we put lone pairs in those hybrid orbitals. That's nice because that keeps it as far away from the other bonds as possible. Okay, this just shows the solution with a nice picture here. So 3 sigma bonds formed by this overlap head-on between the nitrogen sp3 orbital and the hydrogen 1s. The 4th of our tetrahedral hybrid orbitals holds the lone pair, pointed as far away as possible from the other 3 sort of bonding orbitals, and the 3 sigma bonds are shown there. So some of the power of this valence bond theory approach, remember we previously had a rule that things in the second period couldn't violate the octet rule by having more than 8 electrons around them. Why is that? Well, if we were going to have more than 8 electrons around it, that would give us that steric number of 5 or 6, where we would need 5 and 6 orbitals to be used to form the hybrid orbitals. But if n is equal to 2, there are only 4 total orbitals, 1 s and 3 p orbitals, so that's not possible. It's only once you get to n equals 3 where we have 9 orbitals, 3s, 3 3p's, and 5 3d's, that these expanded valence compounds are possible, because we now can mix in these d orbitals in the n equals 3 shell to form trigonal bipyramidal and octahedral electron geometry compounds. So a nice explanation of what was previously just a rule we had. Okay, here's our first exercise. So try to solve these and I'll show the solution in a minute. The first step to solving these is getting the proper Lewis structures. I've shown the first three here, so maybe we'll go through those and then do the last two separately. These are pretty straightforward Lewis structures. Count the electrons, get octets on the terminal atoms, and put any left over on the central atom. PCl5 violates the octet rule, but that's fine because it's in the third period. So now that we have the Lewis structures for these first three, we need to get the hybridization. So to get the hybridization, we need the steric number. So for this first one, there's 4 bonded atoms plus 0 lone pairs, so the steric number is 4. For the second one, 3 bonded atoms plus 1 lone pair is equal to 4 for the steric number. And for the third one, just 5 bonded atoms, so 5 for the steric number. Now to form hybrid orbitals equal to the steric number, so if the steric number is 4, I need 4 hybrid orbitals, that's sp3, which adds up to 4 total orbitals. To form 4 hybrid orbitals on sh3, also sp3. For 5, that next orbital isn't a p orbital because we're out of p orbitals, so this has to be sp3d for the hybridization here. The bond angles, and we may as well do those since we have the steric number. Remember, the bond angles come right from the steric number. So this has a steric number of 4. That's a tetrahedral electron geometry, which is going to mean our bond angles are basically 109 degrees. For ASH3, similarly, steric number of 4, tetrahedral electrons, so also about 109 degree bond angles. But since there's that lone pair, which takes up a little bit more space, we'll say it's a little bit less than 109 as our bond angle. For PCl5, that's a trigonal bipyramidal electron geometry and molecular shape. And just showing what that looks like again, remember this is trigonal bipyramidal. There we have 90 degrees here from the plane to the vertical, and then the triangle here in the plane is 120 degrees. If we wanted to count that one up there, that would also be 180 degrees going from from one side to the other. So if you think you maybe have the idea down now, I'll pause for another second here to give you a chance to do the last two and then show the solutions to those. Okay, these are maybe slightly harder Lewis structures. For SF4, giving the skeleton structure, and then getting lone pairs on all of the outer atoms. Now that we have that, if we look at our electron count, we've used 2, 4, 6, 8 for the skeleton structure, and then we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons for all of these. That leaves us with 2 electrons left over. So remember, you always need to keep track of your electron count. In this case, even though we have octets in all the atoms, we're not done. There's 2 extra electrons, and they have to go on that central atom. So we have that extra lone pair on sulfur. Now we can do the steric number, which is 4 bonded atoms plus 1 lone pair is equal to 5. The hybridization, when it's a steric number of 5, is sp3d. That's our 5 hybrid orbitals. And the bond angles here, again, 5 gives us this trigonal bipyramidal overall structure, and one of those is going to be our lone pair. We put that lone pair in the plane because that's where it has more space, and so the overall structure looks something like this. Remember, the lone pair takes up a bit more space, so this is going to be still about 90 degrees, but these 120 degree bond angles are going to be a little bit condensed due to the lone pair sort of taking up a little bit more space. So 90 less than 120, and we'd still have this 180 degree angle over there. For BRF5, showing the skeleton structure and octets on the terminal atoms, I've used 10 electrons for the skeleton structure, which leaves me with 32 electrons left. Then I put 6 electrons on each of the 5 outer atoms. That's 30 electrons, which leaves me with 2 electrons left over. So same as before, I have 2 leftover electrons that have to go on that central atom, same as SF4. That now leaves my overall steric number as 5 bonded atoms plus 1 lone pair is equal to 6, and the hybridization is sp3d2. That makes 1 plus 3 plus 2 is 6 total hybrid orbitals. The bond angles here are basically 90 degrees. Remember, octahedral just looks like the x, y, and z axes. One of these is a lone pair. These others are fluorines. This is a square pyramidal type geometry, and basically 90-degree bond angles, or 90 and 180 perhaps. Okay, now let's look at a case for a little bit bigger type of molecule and a case where we have multiple bonds. So for ethylene CH2CH2, what's going on in the bonding in that molecule? Well, we have the Lewis structure here. We can see that the steric number of each carbon is 1, 2, 3 bonded atoms. Remember, even though this is a double bond and there's 4 electrons here for the purpose of steric number, it's just 1, 2, 3 bonded atoms on each carbon. So the steric number for each of these is 3. That means each of these is sp2 hybridized. So each of these carbons is sp2 hybridized. When we have sp2 hybridized atoms, what that means is that there's one p orbital left over. What we've done so far, we can say that the sp2 hybrid orbitals are going to be used to form these sigma bonds, the first bond between each atom and the bonds here to the hydrogens. But we don't know what's going on with that second bond. So we do have an unhybridized p orbital on each atom. So if I think about what that looks like, I've got a sort of bond between carbon to carbon using the sp2 hybrid orbitals here. But I've also got these unhybridized p orbitals pointed up and down. What's shown a little bit better here. These unhybridized p orbitals are sitting there. They each have 1 electron in them. Could those overlap to form a sort of side-to-side bond? Yes, and that is in fact what happens. So the side-to-side overlap of our p orbitals are going to be used to form the second and third bonds between each atom, and that will place the electron density above and below the sort of plane of the molecule, or the plane connecting the atoms. What's really powerful about this is it actually gives us a picture of what this molecule looks like in extended 3D space. Remember that we need to have that side-to-side overlap. The orbitals need to be pointed at each other so they can have that side-on overlap. So that actually means the overall molecule has to be this completely flat, planar, rigid molecule. Whereas, according to VSEPR theory, a structure like this would be fine. In this case, there'd be no orbital overlap possible because the orbitals are pointed the wrong directions. And so we can actually say definitively that according to valence bond theory, ethylene has to be planar, which matches experiment. And in fact, we find that because when we have a multiple bond between the atoms, when we would rotate the molecule, we would actually break that second bond. These molecules with multiple bonds can't actually rotate the way that molecules with single bonds. Single bonds, you can rotate around the bond completely freely, but for multiple bonds, that's no longer possible. It would actually break the bond, and that is a nice prediction of valence bond theory that agrees with experiment. So here's our picture of the ethylene molecule. We have these 1, 2, 3, 4, 5 sigma bonds, and then 1 pi bond above and below the plane, which locks the whole ethylene into be this planar geometry. Ethylene here, I'll just show the picture of that. It's a triple bond between the two carbon atoms, and now you've got a sigma bond here, a sigma bond here, a sigma bond here, and 2 pi bonds connecting the 2 carbon atoms. So a triple bond, remember in this case, since it's got 2 pi bonds associated with it, in general that's going to be quite weak. Because single bonds have that better overlap, the sigma bond, these are 2 pretty weak pi bonds that between the 2 carbon atoms, and that does match experiment that acetylene is used very well for welding and other applications where it's useful that this is a relatively unstable molecule and you can release a lot of energy when it's burned. So our summary when we're forming multiple bonds, a sigma bond is just 1 sigma bond. Double and triple bonds still contain that 1 sigma bond, But since we've used up that location, a double bond, the second bond has to be a pi bond, and for a triple bond, the second and third bonds are both pi bonds. So again, sp2 and sp3 and sp hybridized atoms, those three first options here, are the most common cases in organic molecules, which we work with most often in this class. Remember that when we form sp hybrids, we have two unhybridized p orbitals available, so those would be available for forming double bonds or triple bonds to adjacent atoms. For sp hybrids, we have one available unhybridized p orbital, and for sp3 we have no available p orbitals, so if you have sp3 hybridization, there's no way we can form a double bond. Okay, here's our next example. How many sigma and pi bonds are in acetic acid? Okay, so the solution here, if we're counting the sigma and pi bonds, well, each bond contains a sigma bond, so 1, 2, 3, 4, 5, 6, 7. That means there's going to be 7 sigma bonds, because even though this is a double bond, the first bond between these two atoms is a sigma bond. Then for pi bonds, it's only double and triple bonds that contain pi bonds, so I'll separate out the pi bonds here. So this bond here, say, would be our pi bond, and that's just one pi bond. Sometimes people will forget about the sigma bond in a double bond, but you do have to count that one as well. Okay, valence bond theory is incredibly useful in describing organic molecules. So if you go on to take organic chemistry, you'll do this a lot. One thing that we sometimes do is leave off the lone pairs on these organic molecule structures. Remember, though, that we can fill in the lone pairs by using that rule, that we're always going to get the formal charge back to 0. So fill in any missing lone pairs on this molecule. Okay, if we go, carbon isn't going to have lone pairs. It makes 4 bonds, but if we look for the oxygen and nitrogen atoms, each oxygen needs 2 bonds and 2 lone pairs, so we'll add 2 lone pairs here. This oxygen similarly needs 2 bonds and 2 lone pairs. That's also what it needs to get to an octet, right? 1, 2, 3, 4, 8, 8 electrons, 2, 4, 6, 8 electrons. And similarly over here, 2, 4, 6, we're going to need a single lone pair to get nitrogen back to its octet, as shown there. So those are all the lone pairs. That's useful because now if I wanted to describe the bond angles and the hybridization of this oxygen atom, I can. So let's use that to answer the following question for acrylonitrile. Remember to first fill in your lone pairs and then answer each question. Okay, in this case, the only missing lone pair is over here. Nitrogen has 6 electrons but needs 1 more lone pair. To give the bond angles, right, if we want to know the bond angles, we need to know the steric number and therefore the sort of geometry, electron geometry around each atom. So our steric number on this carbon is 3. Our steric number on the second carbon is also 3. Our steric number over here is just 2 bonded atoms, so steric number is 2. Now that I have the steric numbers, I can give the bond angles. So here, since the steric number is 3, my bond angle is going to be around 120 degrees because that's the best way to arrange 3 things as far apart as possible in that trigonal planar type shape. For B, again 120 because the steric number is 3. For C, now there's just 2 things as far apart as possible. That has to be a linear or 180 degree bond angle. Note that it's not always going to be drawn perfectly to scale, so just use the steric number and don't rely on how it's drawn to give you the answer. How many atoms must lie in the same plane? That's a little bit of a trickier one, but the idea here is that because we have these multiple bonds, this molecule needs to be completely planar because we need a double bond up here, and that I guess will also lock this one to be in the plane as well. So all 7. How many sigma bonds and pi bonds? Count the pi bonds first because that's less counting. So one of these 2 bonds is a pi bond, and then 2 of these 3 are pi bonds. So 3 pi bonds in the molecule. All the other ones are sigma bonds, 1, 2, 3, 4, 5, 6. So that brings us to the end of valence bond theory, the first of our 2 key bonding theories. Here's a summary and a brief comparison to molecular orbital theory, which will be our next topic we cover.